I want to show this little GeoGebra document that I've created that gives you a few tools for Minkowski geometry. This would be if you're thinking about special relativity, especially if you're thinking about it in a very geometric way. Um, and so they're all in this. The wrench is what appears on GeoGebra when you've created some custom tools. And so let me just show you. Got a list of these. Some of them are repeated. That's a bit redundant, and I might go back and sort of clean it up a little bit. But probably the first thing you'd want is pick a point and create the null cone, and that just requires, so you click on that tool, and then it's got a little very brief description or instructions there that it says, come on, there we go, that it just creates the null cone through the given point. Now this is all 2 dimensions, of course, so we're going to click that, and then we're just going to click, and there's the null cone. So these are the paths of light rays coming from event A into the future and coming from the past. So that's always something, or almost always something, you want to orient yourself when you have some event A that you know is interesting. Now, of course, I could put a null cone over here and over here, but that's going to get a little bit cluttered. Okay, so what's another thing? Space or time-like units. These are, it's going to give you all of the events that are exactly 1 unit away from the desired point, and those are hyperbolas, or that's 1 hyperbola. It's the 2 branches of a hyperbola. So physically, these are all the events that are 1 unit of proper time away from A in the future, and these are events that are 1 unit of proper time away from A in the past. I think I'll leave that up there. I don't want it to get too cluttered, but we'll leave that up there. Space-like units. These are going to be events that are 1 unit of distance, and of course we're using units where the speed of light is 1. I should have said that already. These are going to be everything that A considers to be 1 unit of distance away. So if these are all the events that are 1 year in the future from event A, and these are 1 year in the past, these would be events that that somebody at A might consider to be 1 light year away. Really, it's depending on what observer is at A and what direction they're going in space-time. So we'll clarify that in a minute. Let's see. So Minkowski magnitude. Well, actually, let's do the Mink quadratic. So this is something that's going to apply to a vector, and so I'm going to actually let me draw a vector first. So let's draw kind of a random vector based at A. Let's have it not be on that units because it's going to be a little too boring. So there's a vector A to B that's time-like. It's going in the future direction. And then I'm going to go to Mink quadratic. And so that's going to be the Minkowski scalar product of that vector and itself. And then it shows up in the algebra window over here, and it might get kind of hidden, and you might have to scroll for it. I don't have it display on the screen. You could have that display on the main geometry window. Right now the default is that it's just giving you the number here. So I'm using the convention that time-like vectors have negative scalar product with themselves, and this is minus 2.35. If I did put it, if that had gone from A to something on the unit vector, that should be a -1. And let me show you a space-like vector, maybe like this, not quite going out to the units. And we'll go back to Mink quadratic. And that's, so now you can see I have to scroll back over to the number section. And that is, it decided to call that B, and that's a small positive number. So that's the quadratic form applied to that vector. Okay, so what else do we have? Now we have magnitude, very closely related to that. It's just the square root of the absolute value of the quadratic form. So let's apply it to the same 2 vectors. Again, you're going to do tail and then tip. of the vector. That's creating a new number. Okay, Mink Mag AB is 1.53. That's the square root of the absolute value of 2.35, or of minus 2.35. So it's always going to drop the sign and take the square root. And I still got that tool activated, so I'll apply it to AC. And again, find that number. And so the square root of 0.52 is 0.72. So depending on exactly what you're thinking about, you might be more interested in the quadratic form, which has the sign in it, or the magnitude, which does not and has the square root. So it's like squared lengths or non-squared lengths for Euclidean, although the sign, of course, is a huge interesting issue. Okay, Minkowski scalar product, you can probably guess what that is. So notice it's saying we're going to select the common base point of two. It's the two vectors you're going to apply it to have to be tail to tail, just to be simple. They're going to have a common base point, and then I'm going to select the tips, and it'll give me the scalar product. So, for example, common base point, and so it's AB and AC. And again, let me find that. Okay, so this Minkowski scalar product of the AB and AC is 1 here. Notice they look, visually, they look approximately perpendicular, but that's our Euclidean intuition. They're absolutely not orthogonal in the Minkowski sense. So this is nowhere near 0. If they were 0, AC would have to appear on the line that's flipped symmetrically across that null line from AB. So it'd have to be going more up in this direction. Okay, so speaking of which, let's create some Minkowski perpendiculars. So Mink perp left, as it says, you can see it says creates Minkowski orthogonal vector and the tip point of that vector given a tail where you want to base it and the tip of the original vector. So, and specifically the left is that it reflects across the left moving null line. So I'll show you that. So got that selected. And so it's going to be based at A and it's going to be perpendicular to AB. Aha, so I'm just flipping across that northwest southeast null line. And so AD will have the same Minkowski magnitude and is guaranteed to be Minkowski orthogonal to AB. And if you want the other one, that's obviously Mink perp right. So it's going to be a vector based at A and perpendicular to AB. So this is exactly what I was sketching out before. That AE, that is a vector that's space-like, moving to the right, and is Minkowski orthogonal to the vector AB. We can double check. Let's take the scalar product of AB and AE, and that's go back to our numbers. Aha, and that's 0. Okay, so that's cool. All right, and then the most intricate thing is Mink proj. So this is super useful, Minkowski orthogonal projection. So we're going to get a base point, a point along the projection line, and then you just need the tip of the input vector. So it's best demonstrated just by an example. So I'm going to, let's first do it in a way that's pretty intuitive. I'm going to have A be a base point here. F is going to, oh, actually, let's see. Let's actually go back. No, let me create that line first. Let me just get the line first real quick. Okay, so let's just say it's vertical, so it's going to look more intuitive there. But I think I want to make sure that that's kind of not in the way. Let's make the line pretty close to vertical and determined by F. So that will be the projection line, and then we'll move it in a minute. Okay, now proj. So okay, so here's our base point. I'm going to determine what line I'm going to be projecting on, and then I already have the base point of my vector, so I just need the tip. Okay, so that looks just like Euclidean projection. Now that's a little misleading because I picked a very special direction here. But what does it create? it created two vectors, created AG, which is the projection of AB onto this line AF, and GB, which is the orthogonal part. So the properties are that AG plus GB should be AB, original vector, that AG is along the line AF that we specified, and that crucially AG and GB, or equivalently AF and GB, should be more Minkowski orthogonal. So now let's use the power of dynamic geometry software. What if I was projecting onto a different line? Okay, now it doesn't accord with our Euclidean intuition, but it's still true in all of these cases that GB is orthogonal to the line I'm determining by AF. Just doesn't look at it in a Euclidean sense. And so that is a very useful tool for doing orthogonal projections. And then you can do things like components. The component of AB along the line AF is just going to be, well, the absolute value of it is just going to be the Minkowski magnitude of AG. So we could go to here and we could say, oh, what is that component number? Of course, that's something we have to bring back up to the, yeah, so Mink mag of AG. So 1.86 is the Minkowski component, although minus any sign here, of this vector AB along this direction determined by the line. Anyway, that's all the tools I put in for this tool, this page, I guess, diagram, I guess. And I might make another video where I go through like a classic, drawing a classic diagram like twin paradox or like a train going through a station with these tools, but I'd have to practice that first.